Good afternoon. During the first part of the class of today, we will review the definition of inner product of vectors in Rn, the definition of projection of a vector along another vector, the definition of projection of a vector onto a subspace of Rn, and we will see how to use these tools for studying the relationships existing between a curve and its first and second order derivatives. Okay, let's start from the definition of inner product. The inner product or dot product of two vectors x equal x1, x2, x3, xn, y equal y1, y2, y3, yn of Rn is given by this formula x1 y1 plus x2 y2 plus x3 y3 plus xn yn. The inner product has the following properties. Suppose that x, y, z are vectors over n, and lambda and mu are real numbers. Then the inner product is symmetric, so this means that the inner product of x and y coincide with the inner product of y and x. Two, the inner product is bilinear. This means that lambda x plus mu y multiplied by z is equal to lambda the product of x and z plus mu multiplied by the inner product of y with z, and x multiplied by lambda y plus mu z. This is equal to lambda x y plus mu x z. So this is the bilinearity. Property number 3 says that the inner product of a vector with itself is the length of this vector squared, and it equals 0 only if x is a zero vector. This means that all of its components are equal to 0, and The last one is known as Schwarz inequality, and it says that the absolute value of the inner product of two vectors is smaller than the product of the lengths of these two vectors. The inner product of two vectors can be defined also in a geometric way. So suppose that x and y are vectors in Rn, and theta varying in the range 0 pi is the angle between them. Then the inner product of x and y can be defined as the product of the length of x times the length of y times the cosinus of. This definition can be used for defining the angle between two non-zero vectors It's clear that we have the angle between x and y according to this formula is given by the arc cosinus of the quotient between the inner product of x and y and the product of their lengths. This is a symbol that we use for the angle between the vectors x and y. The vectors x and y are orthogonal if the inner product is 0. They are parallel if one of them is a scalar multiple of the other. So for example, y is equal to lambda x with lambda in R. What are the consequences of the orthogonality on the value of the angle theta between two vectors? And what are the consequences of parallelism of two vectors on the value of the angle theta between two vectors? If x, y are non-zero vectors, then the angle between x and y is pi over 2. Sorry, I mean, then if x and y are orthogonal, then the angle between x and y is 0, and they are parallel, then the angle between x and y equals 0 or pi. The inner product is useful for introducing the components vectors in the direction of a given vector, and projections of vectors in the direction of a vector. So I have to give you the definition of component and projection. So definition which actually is a proposition. At the same time, because a part of the statement I will give you must be proved. So if x, y are vectors in Rn and length of y is non-zero, then there is a unique way of writing x as sum of two vectors having the following properties. Vectors are denoted by x parallel and x orthogonal. You can guess why I am using this notation. Where x parallel is parallel y and x orthogonal, of course, is orthogonal to y. X parallel is called the projection of x direction of y. The sine length of x parallel. So the expression sine length means that the length can be also negative. That is the number lambda in R such that x parallel is equal to lambda times y over its length is called component of x, the direction of y. Okay, let's try to make a picture in order to have a better understanding of what I'm saying here. So suppose that theta equal to the angle between x and y is acute, then suppose that this is x, suppose that this is y, and this is theta. What is x parallel and what is x orthogonal? It is clear. You have to draw a segment of straight line starting from the tip of x and which is orthogonal to y. Then you will get two vectors. The first one is this. This will be x orthogonal. And the second one is this. This will be x parallel. What about instead when the angle is obtuse? Suppose that this is x. Suppose that this is y. And this time, if you draw a straight line starting from the tip of x, which is orthogonal to y, you get this. And now we have two vectors. The first one is this, orthogonal to y. This will be x orthogonal. And the second one is this. This is x parallel. And what is the difference between this case and this case, where so theta is obtuse? So difference between these two cases. If theta is acute, then the component of x in the direction of y is positive, instead if theta is obtuse, component is negative. Why it is this? Because the component is the number lambda which appear in this formula. So this is the component. In the first case, when theta is acute, we have that the x parallel and y point in the same direction. This means that lambda is positive. In the second case, where theta is obtuse, sorry, I made a mistake. Theta is this angle here. Sorry. And the component, x parallel and y point in opposite directions. This means that lambda is a negative. Okay, let's prove this proposition. So we have to prove that x is equal to x parallel plus x orthogonal with x parallel to y and x orthogonal to y. Okay, so in order to prove this statement, we define x parallel as lambda times y over length of y. Observe that this is the point where we are using the hypothesis that the length of y is non-zero. And x orthogonal as the difference between the vectors x and x parallel. Okay, clearly by this definition, x parallel is parallel to y. Why? Because x parallel is a vector given by a number lambda over length of y times y. So x parallel and y are parallel. It remains to prove that there exists lambda such that x orthogonal is orthogonal y. Okay, this is very easy. We have to impose that the inner product of x orthogonal with y is equal to 0. But what is x orthogonal? X orthogonal is being defined as the difference between x and x parallel, and the x parallel is given by this formula. So we can write x minus lambda over length of y times y multiplied by y. Then by bilinearity, this is equal to xy minus lambda over length of y, the product of y itself, and this is equal to xy minus lambda over y times length of y squared. This is equal to xy minus lambda y. And now it remains to solve the equation 0 equal to inner product of x and y minus lambda length of y, and we get lambda equal to xy divided by the length of y. So we found the value of lambda such that x orthogonal is orthogonal to y, and we also proved that lambda is unique. We also proved that lambda is unique. So this means that the decomposition x equal x parallel plus x orthogonal is unique. Okay, we call component of x in the direction of y, the inner product of x with y divided by y. It is exactly what we got here. Observe that there is a special case this is equal to x y if the length of y is 1, and we call projection the vector given by x multiplied by y over y squared times y. How you get this one? You just need to multiply the component by y over its length, and you will get the projection. Also, in this case, there is a special case. This is equal to x y times y if the length of y is 1. Okay, in the sequel, we will need to project vectors in the direction of an element of collections of vectors. And we will look at the special collections of vectors, collections which are orthonormal. So let's give a definition. A set y equal to y1, y2, y3, yk of vectors in Rn is said to be orthonormal if each vector in Y is a unit length and the inner product of Yi with Yj is 1 only if I is equal to j. In all other cases it's 0. It is very easy to prove that every orthonormal set is linearly independent So I will give you the idea of the proof of this statement. So the vectors in the collection in the set Y are linearly independent if sum from 1 to k of lambda I Y I 0, if and only if lambda I for any I 1. The idea is to use this property and in order to use this property what you need to do multiply sum on I from 1 to k of lambda I Y I by the vector yj, and deduce immediately that lambda j the statement follows from the fact that j varies in the set of indices 1, 2. Okay, what happens now if the number of vectors coincide with the dimension of the space we are considering? Do you remember we are considering vectors, k vectors in Rn? In this case, we say that the set of y, which consists of y1, y2, yn, is a basis of Rn. More precisely, it is an orthonormal basis. Why this is a basis? Because these vectors are linearly independent, we proved it before, and you have a number of them which is equal to the dimension of space you are considering. Of course, if k is more than n, we can also say that y is an orthonormal basis but not of Rn, but only of the vector space they span. So I will write of its span. If this is true, we have the following property. Every vector x belonging to span of y, so I repeat one more time, span of y means the vector space spanned by the vectors in y, can be written in a unique way as a linear combination so In this case, we can write then something like x equal a1 y1 plus a2 y2 plus an y. Now let's ask ourselves, what is the component of x in the direction of yi for h prime. We are considering an orthonormal basis, so the component of x using the formula I gave you in the special case of vectors having length equal to 1 is equal to x times yi, and this is equal to the inner product of sum of ai, sorry, let's write aj yj with j running from 1 to n to 1 to k multiplied by yi, and using multilinearity and the fact that the vector we are considering form a collection which is orthonormal, we get just a I. So this formula said that if we work with an orthonormal basis, then the coefficients are j in sum aj yj. This is a formula expressing x as a linear combination of the element in y coincide with the projection of x in the direction of y j, j equal 1 to k. The next result I will present is the generalization of the proposition we saw before, the one about the decomposition of a vector into two parts. The first one is a vector parallel to a given vector y, the second is a vector which is orthogonal to a given vector y. And in this case, we can decompose a vector x into two parts. The first one is a vector which lies in a collection of vectors, and the second is a vector which is orthogonal to any element of the collection of vectors. Okay, so we have definition. One point. Also in this case, this is also a proposition because the part of the statement must be proved. So if nu contained in Rn is a subspace, and X is a vector in Rn, then there is a unique way of writing X equal X parallel plus X orthogonal where X parallel is contained in nu and X orthogonal is orthogonal to any vector in X orthogonal is of the projection of X onto nu, and if Y equal to Y1, Y2, Yk is an orthonormal basis of nu, then we have a formula for X orthogonal. Sorry, for X parallel. X parallel is equal to the inner product of X Y1 times Y1 plus X Y K multiplied by Y. And exactly as before, we have that the coefficients which appear in this linear combination are exactly the component of X in the direction of the elements of Y. So I will write it here, even though you understood. So the coefficients of this linear combination are the components of X, the direction definition of y1, y2, y. Okay, I don't prove this proposition. I leave the proof to you as an exercise, and instead I want to show you a simple example. So what is the orthonormal basis that we use the most often for Rn? This basis has a name, is called standard orthonormal basis. This basis is given by the vectors E1, E2, En, where E1 is the vector whose components are 1, 0, 0, 0. E2 is the vector whose components are 0, 1, 0, 0. And we continue this way until En is equal to 0, 0, 0, 1. So, for example, if you take maybe let's use this, which is better. If you take n equal to 3, then you get E1 equal 1, 0, 0, E2 equal 0, 1, 0, E3 equal 0, 0, 1. And if you take a vector like a vector x like 5, 3, minus 2, what can you say about its components in the direction given by E1, E2, E3? Very easy. Of E1. This is given by the inner product of x and E1. This is equal to 5. You can continue. Component in the direction of E2 is given by x 2, and this is equal to 3. And the component direction of 3 is x 3. This is equal to negative 2. And now let's try to determine the projection of x onto the subspace spanned by E2, E1, E2, and this is given by x comma E1, 1 plus x comma E2, 2, and this is equal to 5, 3, 0. Why? Because x E1 is equal to 5, x E2 is equal to 3, and then E1 is given by 1, 0, 0, and E2 is 0, 1, 0. So it's easy to see that you get this result. Now let's use the tool we introduced for studying a few properties of curves. Okay, let's consider this lemma. Lemma 1.16, which says the following. Suppose that gamma beta defined on I with values in Rn are parameterized curves. And C from defined on I with values in R is a smooth function. Then the following identities hold true. 1, the derivative with respect to t of the inner product of gamma t with beta t, this is equal to the inner product of gamma prime with beta plus the inner product of gamma with beta prime. This is the first one. The second one, dt of ct times gamma t, this is equal to c prime t gamma t plus ct gamma prime t. The proof of These identities is very easy. In order to prove it, so I will give you the real proof. Suppose that gamma t is equal to x1 t, x2 t, xn t, and beta t is equal to y1 t, y2 t, yn t. So this means that x1, x2, x3, xn are the component function of gamma, and the y1, y2, y3, yn are the component functions of beta. Then what you have to do is just to replace them into this formula, and you compute the derivative with respect to t component by component, and you apply the rule for the derivative of a product of functions, and you will get immediately these two identities. I would like instead to present to you one proposition proposition 1.17, which says the following: let gamma beta from I into Rn be a pair of terms then we have the following two properties. One, if length of gamma is a constant for all t in I, then gamma prime of t is orthogonal to gamma t for all t in I. And the second one, if gamma t is orthogonal to beta t for all t in I, then we have the following identity. The inner product of gamma prime t beta t is equal to negative linear product of gamma t with beta prime of t for all t in I. Remark: the hypothesis of the proposition of the hypothesis of the proposition hold true So are satisfied? If the collection of vectors gamma t beta t is orthonormal for all t. Why? Because if this collection is orthonormal, then this means that the length of gamma t is always equal to a constant, precisely is always equal to 1. And it is also true that gamma t is orthogonal to beta t. Okay, let's see how to prove this proposition. So, to prove one, we have to prove that, so show that if length of gamma is equal to c for all t in I, then gamma t and gamma prime t are orthogonal, which means that gamma times gamma prime t. Okay, how to prove this? We know from one of the identities I presented at the beginning of the class that if gamma t is a constant, then since gamma t square is equal to gamma t multiplied by gamma t, we have gamma t of gamma t equal constant. It's better to erase the backboard, otherwise able to read. Then the derivative of gamma t is will be equal to 0, and by lemma 1.16 this is equal to gamma t gamma prime t plus gamma prime t and this is equal to twice gamma t gamma prime t by symmetry. This is the end of the proof because this says gamma t gamma prime of t equal to 0. because here you have that the left hand side is 0. Now we have the proof of the second part. By hypothesis, we have that gamma t, beta t, this is 0, because gamma t and beta t are orthogonal. Then once again by lemma 1.16, we have that 0, this identity follows from the fact that this is 0. This is equal to gamma prime t beta t plus gamma t beta prime. This implies that gamma prime t beta t is negative gamma beta prime. Okay, for today that's all. Thank you for your attention.